Hey everyone, this video we're going to look at sketching surfaces in three-dimensional shape. We will be looking at cylinders and quadric surfaces. The first two pages of this video are just copied right out of your e-text. Please do not attempt to memorize this unless you just absolutely want to. These can be found in your e-text in section 6 of chapter 11. And this is for the Larson Edwards book, 7th edition, that we're using for Calculus 3. I do not own any of these. All rights and privileges are for Larson and Edwards. The main thing with this section is recognition. For example, the ellipsoid, which is basically like a, football shape, something to that effect. Notice that X, Y, and Z are all squared terms, and they're all on one side of the equation equal to 1. Everything is recognized by format, so when I mention referring to the first two pages, it's simply that. I'll show you with some examples how to recognize which type. For example, if everything is set equal to 1, but you have one term out of the three that's negative, then that's called a hyperboloid of one sheet. The term that's negative is the axis that this shape runs through, or the direction that it goes. With an ellipsoid, it's totally closed in. The bottom numbers A, B, and C represent, for example, if this happens to be a 9, square root of 9 is 3. In the X direction, it would run 3 units in each direction. Maybe the Y squared has a 16 underneath. Square root of 16 is 4. So you would have 4 units in the Y direction each way from the origin. Same thing for Z. Maybe that's a 25. Then you would run 5 units up and down from the origin. Ellipsoid was when all three terms are positive, equal to 1. Hyperboloid, when all three terms are equal to 1, but one of them's negative. And then a hyperboloid of 2 sheets, which would be this type of shape, is when 2 of the 3 terms are negative. The one that's positive will be the direction that these hyperboloids run. Since Z is positive, they open up and down along the Z axis. These sheets are very informational, so I highly encourage you to pull these up under your e-text. Again, it's section 11.6, Surfaces in Space. This is the second sheet, and what it'll look like, they are 2 consecutive pages. From a physical book, they're pages 800 and 801. Now, the elliptical cone with a pointy edge, not a rounded edge, instead of 1, you're going to have this thing equal to 0. All the variable terms on one side equal to 0. The one that's negative will be the direction that this thing runs. The directrix, I believe, is what it's called. Let's jump into some examples. We're not going to hit every single one, but I just really want to show you how to get involved and recognize. It's all about recognition. I'll never ask you to hand sketch one of these. All right, here we go. All right, so let's start with this example. Let's match the equation with its graph. Now, those first 2 slides, those are in your Google Drive folder for your class. Feel free to just visually access those with your phone or iPad, computer, or if you want to print them out, absolutely up to you. I do want to notice some things with this one. We have equals 1, and so that corresponds to the first page of the video, not the second one. all three variable terms are on one side and they're all positive, that's a dead giveaway that you have an ellipsoid. Now, what I was talking about earlier, these bottom numbers, since that's 3 squared, and I'm just going to lightly sketch this in, very lightly. 9 is 3 squared, so in your x direction, you have 3 units away from the origin. In the y direction, 16, that's 4 squared. The y direction, you would go 4 units. And then finally, in the z direction, 9 is 3 squared. So you would peak at 3 and negative 3. So this is a three-dimensional object that has pretty specific amounts of travel from the origin. So the first thing you want to recognize is all variable terms on one side equals to 1. That takes you to page 1 of the Google Drive folder page for this particular section, or from your e-text, it's the first one. And then the second thing is these denominators. Even if something's like a 7, then you would just approximate the distance as square root of 7, which would be between 2 and 3. But these numbers here tell you how far from the origin to travel in each of the 3 respective directions. Let's switch over and let's look at 15x squared minus 4y squared plus 15z squared equals negative 4. If we bring the negative 4 over, then we'll just have a constant equal to 0. None of the pictures from the first 2 slides, specifically the second slide, where you don't have room for a constant. You have room for 3 variable terms equal to 0, but you don't have 3 variable terms and a constant equal to 0. So it doesn't fit that format. Let's look at what it does fit. I am going to go through and divide everything by negative 4, because what I want to do is turn that last position, that negative 4 that's on the right of the equation, I want to turn it into a positive 1. Now, since this is an equation, it is totally appropriate to divide all your terms by the same value. All right, so I'm going to switch over to black. Here we go. Carrying this down to the bottom, we have negative 15 x squared over 4 plus y squared minus 15z squared over 4, and that'll be equal to 1. When you go back to the first 2 pages of this particular video, excuse me, and again, in the Google Drive folder, it'll be the first 2 pages of all of these 9. We notice that we have 2 negative terms and 1 positive term, and it's all 3 variables are on one side equal to 1. So when 2 of the 3 are negative, you have a hyperboloid of 2 sheets. Hyperboloid of 2 sheets. Now, I'm going to write these with the positive term first. You don't have to, but to get it to match up okay, I'm going to write it where I've got a positive term out front. one positive, two negatives, so hyperboloid of two sheets. The axis of the hyperboloid will correspond to the variable whose coefficient is positive. There is no trace in the coordinate plane perpendicular to this axis, so the y-axis is the one along which all the action happens. Notice here we have the y-axis, that's the positive term, and we have a smooth, I don't want to say cone, but it's sort of conical shaped, but you have a smooth bottom instead of a pointy bottom. And it runs each way in the y direction. If z had been positive, then you would flip this up and you would have a hyperboloid of two sheets that went up and down. Y squared equals 4x squared plus 9z squared. This one we've got to be careful looking at because we don't have all terms on one side. If we get it there by moving the y squared over, then what we're going to see is 4x squared minus y squared plus 9z squared equals 0. Because when we move y squared over, I'm going to just move it over, pop it in the middle, it'll go from positive to negative. Now, when you line this up with the second page, you will find that it matches an elliptic cone. An elliptic cone. The axis of the cone corresponds to the variable whose coefficient is negative. So let's look at that. We've got y squared, and that's the negative term. Elliptic cone, we do have cones, but they have sharp instead of rounded edges. So we have a cone. Again, the term that's negative is the axis along which this will run. (4x squared minus y squared plus 4z equals 0). We have all three variable terms, but one of them is only linear. It is not quadratic in nature. It doesn't have a square. From page 2, this will either be an elliptic paraboloid or a hyperbolic may be the right way to say that, paraboloid, hyperbolic or elliptic. The way you tell the difference is you isolate the variable that only has a power of 1. Once you've isolated, then you will be looking for a plus or a minus sign between the two variables that are on the other side. So let me hop in here real quick. That was a lot of words. Okay, I'm going to leave the 4z where it is. I'm going to take the 4x squared over. It'll go positive to negative. And then I'm going to take negative y squared over, and it'll go from negative to positive. The order doesn't matter. I'm just particular in writing it this way. Divide both sides by 4, and you'll get z equals y squared over 4 minus 4x squared divided by 4 is just an x squared. Once you've got z, and I'm going to go ahead and put this over 1 just to give it some context and a little bit of size appropriation. Going back to the original, z was not squared. It was to the first. So if you catch one of these three variables, it's only a first power, isolate it. Now that we've got it isolated, there's a minus sign between our other variable terms. Well, when that's the case, it's a hyperbolic paraboloid. It looks like a saddle. Like if you were to put a saddle on a horse, that's what it would look like. In the y direction, this thing will run 2 units away from the origin. And in the x direction, it will go 1 unit away from the origin. It's very hard to see this one visually, but that minus sign is the giveaway. The variable that you isolate is where you would sit if you pretended this was a saddle. The z-axis is where you would come down and sit. Describe the surface. The x-coordinate is missing. So far we've had x, y, and z, all of them thrown in. Occasionally one wasn't squared, and that's okay. But for this one in particular, we are missing an x-coordinate. So it's a parabolic cylinder with the rulings parallel to the x-axis. Now that's a little bit of vocab here. Also, let's note the generating curve is a parabola. Let's look at what that means. I'm going to isolate z and that'll give us z equals 4 minus y squared. Now, in terms of if we were just doing this in 2 dimensions, like for example, it would be y equals 4 minus x squared, then what we would have, and again, this is just like back in the good old college algebra days, if this were y equals 4 minus x squared, you would have an upside down parabola that hit the y-axis at 4 and just was an open downward parabola. When you extend this to 3 dimensions, what happens is, look on this graph in particular, the variable that's missing is x. Notice that if you take the parabola from up here in the top right of your screen, take its basic shape, but elongate it, then what you get is a whole series full of those downward opening parabolas. The variable that's missing is the axis along which that generating curve will open. Okay, so the downward opening parabola is the generating curve, and the axis along which it runs is the rulings. Let's look at an example of a quadric not centered at the origin. Some of these, or in fact all of them before we get to this example, has been centered at the origin. Now, it's easy to recognize when you have a case that doesn't, because you'll have a whole bunch of x, y's, and z's scattered out. You may even have a constant, but nothing's going to look organized. Nothing's going to be grouped nicely and squared. So in this kind of situation, what you want to do is gather your like terms. So x squared minus 4x, leave a little bit of space, collect your y terms, and then finally collect your z terms. If there's a constant, move it over. So 3, when it goes over, becomes negative 3. make sure that your squared variables are clean or have a coefficient of 1. That's true for the x squared and the z squared. Y squared has a coefficient of 2, so I'm going to factor a 2 off of the y terms. And then now we're going to use a technique that's called completing the square to organize each variable into a squared quantity. So let's remember how to do that. I've got these color coded, so x will be in blue. When you complete the square, you take half of the term in front of x, which is -2. -2 squared is 4, so essentially you're adding 4 to both sides. If you were to FOIL this out, it would have a +4 at the end. If you do a +4 on the left, you got to balance it out with a +4 on the right. With y, half of 2 is 1. 1 squared is 1, times 2 is 2. With z, half of -2 is -1. -1 squared is +1. So each time you complete the square for x, y, and z, you just be very careful to add the squared value on each side. If there's a number you had to factor out, be sure that once you square, you multiply by that number as well. So that's why this one was actually a +2. Everything on the left side is now organized into x, y, and z, collected nicely. -3 plus 7, that's 4. We have all 3 variable terms on one side, and they're all added. So this is an ellipsoid, but it's not official yet until we make this a 1. If you divide all the way through by 4, 4 divided by 4 is 1. This group divided by 4. This group divided by 4, the 2 over 4 becomes a 1/2. And then the x category divided by 4. I'm going to default to the e-text again. Because you have all 3 variables on one side equal to 1 and all of them are positive, this is an ellipsoid centered at 2, -1, +1. You have to go opposite of your parentheses to get the center. I can't draw that very well, so this next slide is just what this ellipsoid looks like. You have the ellipsoid centered at the point 2, -1, 1. And this bubble here just shows the result of our hard work on the previous slide. So this is exactly what we got when we completed the square, divided all the terms by 4. But this is it's sort of an egg shape is what it is. It's an egg shape. But that's the center. Remember to go opposite. 2, -1, +1. And then in the x direction, which is this way, you will go 2 squared, 2 units, front and back. In the y direction, you will go square root of 2 units, and that'll be the left and the right direction from the center. See how it's not quite as wide as it was front to back. And then in the z direction, 4 is 2 squared. You'll go up 2 and down 2. Notice if you add 2, you go to 3. If you subtract 2, you go to -2. Excuse me, -1. Again, I don't expect you to be able to draw these very well. If you're very artistic, though, you can. Let me know if you have any issues with this section. Reach out by phone, email, stop by during office hours, and I will do my best to help you out. Thank you.